this presentation, we give some background information on black holes and general relativity, and how the observational part of this experiment, the laser interferometer gravitational wave observatory, how that works, and the simulation results and future scientific observations for LIGO. We use the acronyms because it has long names. So introduction, why study this? Well, gravitational wave astronomy is like a relatively new branch of astronomy, and we're trying to study gravitational waves, and I'll explain what that is in a minute. And it turns out that one of the strongest sources of gravitational waves are binary black holes, and even though they're still hard to detect. And the goal is to learn about gravitational waves and their sources, and provide the simulation data to LIGO, which is located in Louisiana and Washington. Okay, here's some background information on black holes. They are formed after a high-mass star's core collapses, and the star must be at least about 8 solar masses, so that song, Black Hole Sun, is not accurate. The sun can't turn into a black hole. So black holes have high mass and low radii. As you can see the equation for the Schwarzschild radius, the number in the denominator, which is c, the speed of light, is a very big number, and the number in the numerator, capital G, is a very small number. So radii are comparatively small to the mass. Like, for example, a black hole that is about 3 solar masses has a radius of about 15 kilometers. So something that weighs 3 times as much as the sun is only 15 kilometers in radius. That's pretty dense. And 2 important parts of a black hole are the event horizons and a singularity. The event horizon is sort of like the point of no return, because if you go past in the event horizon, you can never go back. And this is because the escape velocity at that radius is greater than the speed of light. And the speed of light is 2.998 times 10 to the 8 meters per second, so it's pretty darn fast. And there's no escaping the event horizon. When r is equal to that Schwarzschild radius, you can't go back. And so all the mass in the black hole is concentrated in an infinitesimally small point called the singularity. So this is some information about binary black holes, which are 2 black holes orbiting each other. There are 3 important phases of this: in spiral, merger, and ring down. And when black holes begin orbiting each other, they emit gravitational waves. And because of this energy loss, the radii of their orbit decrease, and the speeds of their orbits increase. So gravitational waves are generated. The amplitude increases during the in spiral. You can see in the graph. And also, if black holes are spinning while they're orbiting it, it causes the orbit to recess, meaning that the axis of the orbit is slowly tilting. The second phase is merger, and that's when the 2 black holes fuse into one. And the gravitational waves kind of have a messy amplitude. It kind of fluctuates a lot. This is like the not so nice part of the graph. And the third phase is ring down. It's when the black hole is one and it goes into equilibrium spinning, and the amplitude dies down really, really quickly. And as you can see, the amplitude decreases after the ring down phase very fast. So here's some information on general relativity. And the reason we use this instead of Newtonian physics is that during high mass and high velocity scenarios, Newtonian physics does not describe what happens in nature. So we use more of the Einstein's physics, which is general relativity. And so instead of 3 dimensions, like length, width, height, we use a 4-dimensional space-time. And oftentimes, space-time is represented as like a rubber sheet. And gravitational waves are like ripples in space-time. So I can go back a couple slides. you can see that the black holes are sort of like rippling spacetime. So, yes, so in the presence of gravity, spacetime is not Euclidean, that means it's flat. So it's not flat in the presence of gravity, so gravity distorts and bends space-time a lot. And gravitational waves, it turns out, have frequencies in the range of 20 to 20,000 hertz, which coincidentally is the hearing range for humans. So this is what black holes would sound like. Play the sound. It's not playing. Yeah, that's what they would sound if they were sound waves. But technically you can't hear them because they're not longitudinal sound waves, they're transverse quadrupolar waves. But just for fun, that's why we made this like little audio. And another thing about general relativity is that there are no analytical solutions to Einstein's equations. So we use numerical relativity to approximate the solutions. And to emphasize how long Einstein's equations are, it takes about 100 pages to write them out completely. So this is obviously why we use computers. Okay, and this is the observational part, which is not my domain, but we have updates on this site a lot. It's called the Laser Interferometer Gravitational Wave Observatory. And it has two locations, one in Washington, one in Louisiana. And it's a Michelson interferometer, which means that there is a beam that is split into two at the vertex of the interferometer, and the two beams are meant to destructively interfere at the detector, and destructive interference means it cancels out. But when a gravitational wave passes through the interferometer, it changes the length slightly because it changes the space-time, and so the two beams will be out of phase, and we can measure how out of phase the beams are. And here is the equation for the signal, and you can see that it's sinusoidal because of the cosine, and it's inversely proportional to distance, that's a d, and the amplitude, AFT, is proportional to the frequency of the wave to the 2/3 power. And so here are the results for the simulation that I did. It was we simulated two black holes, each with one solar mass, that were spinning very slowly, but they were still spinning, and they had 12 orbits. So I'm going to play this. If you look very carefully, you can see the precession because the circles aren't all so here are the results of the simulation, the gravitational waves that were generated from this. Okay, and a couple things about the units. These are units used in general relativity, where g, the Newton's gravitational constant, and c, the speed of light, are both set equal to 1. So it's a bit different than SI units. So basically, you can see that this graph looks a lot like the previous one, this one. See, you can identify the in-spiral merger and ring down in this graph. So this is the part, you can see the amplitude increase, and that's in-spiral, and this very small section of just chaos, the merger, and at the very end, it's ring down. when we approximate gravitational waves, we would like to extrapolate for an observer that is far away from the source, since binary black hole collisions happen like millions of light years away from Earth. So we're trying to do this at very large distances from the source. And as you can see, the amplitude is inversely proportional to the distance from the source. So it's proportional to 1 over r. And I did a little line of estimate for the amplitude, and as the radius approaches infinity, the amplitude approaches 0. And here are some future ways to study gravitational waves. Advanced LIGO, it is predicted to start in fall of 2015, and the sensitivity of the interferometer increased by a factor of 10, and the volume for data collection increased by a factor of 4. So if you compare the initial and advanced LIGO, the advanced LIGO is the bigger sphere. Advanced LIGO really has an advantage because with a bigger volume for data collection, you could have more candidates for gravitational waves. And hopefully things will go well when we provide our simulation data to LIGO. And here are the sources.
Questions for Joy, please?
Yes.
So do binary black holes have to be spinning?
Usually they are. Spinning black holes are called Kerr black holes, and non-spinning ones are Schwarzschild. But usually they have spins of like less than 0.9. It gets really complicated when the spins are very high, though. That's why I did a very simple simulation with a very slow spinning one.
Okay.
Did you have any experience with this topic prior to starting this hour?
I only knew a very small amount of general relativity and some stellar astronomy, but I had no experience computer programming prior to this, so it's pretty big. Yeah.
That's great. Learned a lot. Any other questions?
Was this hard?
Well, it went sort of as expected, a bit faster than expected, so I guess it was okay.
What do you think of the supercomputer?
It had some bugs and everything, but it finished its job faster than we expected, so that's a good thing.
Okay.
The person asking you those questions, by the way, ran the LIGO summer program for students for, what, 10 years?
I beg your...
I thought Ken asked.
No.
You got
Oh, I'm her...
Next to him.
Oh, I'm her father, so I kind of watched this come together, so...
Wonderful, wonderful. We love it when families